So now what happens? So how do we apply this to a general robot? Well, a general robot has several joints, right? So in the case of independent joint control, what do? We pretend that every joint is a mass spring damper system. Okay. And so if we want to move the robot from here to here, okay, here's our initial, here's our final. We want to move from here to here. We pretend we pretend each joint is a mass spring damper system. Okay. We find the gains, Kp and Kd, for each joint, okay, that achieves critical damping. And hopefully, if we choose the gains properly, the robot will go from A to B, okay, in a critically damped way. Okay. So is that a good idea? Well, it depends on how you choose the Kp's and Kd's, right? And also, what's the assumption we're making? We're assuming that each joint is a mass spring damper system independent of the other mass spring damper systems. Okay, that's not a very accurate assumption, right? Because when in our arm, what happens here influences what happens here and here. Okay, so these are not independent. Okay, but we're making that assumption anyways. And so, the assumption's not accurate. Okay, Kp and Kd requires a lot of work to find the right values. So it seems like this method is going to be difficult to make it work well, right? It's not easy, but in fact, this method is still used a lot, okay, in industry, in practical settings. This independent joint PID control is in fact a very effective way. Now there are better ways, but it's an effective way that people use to control industrial manipulators. Okay. All right. So now let's look at the nonlinear case. Okay. So now let's consider this. Remember this? Okay, so consider this again. All right, so the equation here was tau equals large M theta 2 dot plus mgr cosine theta. We're going to add friction here. Okay, so let's say there's some term b theta dot. Okay, so this has friction and gravity here. Okay, so let's again consider the same problem, okay? Moving the robot to some desired set point configuration, okay? So how can we use this approach for this problem? Well, here's how it's done. Okay, so assume, well, set tau to be of the form alpha tau prime plus beta. Okay, and now we have to choose alpha and beta. Okay, so for this particular problem, we set alpha equal to m, large M, and we set beta equal to the rest. Okay, so it's b beta dot, let's see, yeah, plus mgl, or mgr cosine theta. Okay, and then now we choose tau prime, the control, to be PD control. Okay, so this would be minus Kp times theta minus kV times theta dot. Okay. All right, so for critical damping, okay, for critical damping, we want, let's see, what was the relation? It was, okay, so work through it. You'll see that we need kV to be 2 times square root of kp. Okay. All right. So this is actually a slightly different idea. Well, it's an extension of this previous idea of PD control. Okay. So what we're doing here is we're in fact kind of subtracting out the sort of nonlinear dynamics here, and then applying a PD control law. Okay. All right. So we can carry this idea further and apply it to general, n-link open chains. Okay. We'll do that next time. Another thing I want to also point out, just make a remark here, and fill you in on the details in the next class, is this critical damping relation. Okay. So for critical damping, all we require is that kV and kp obey this relationship. Okay? So that means that we can make kV and kp arbitrarily large. Okay? So if you think about what large gains mean, okay? So remember, this is applied to the x dot term. This is applied to the x term. Okay? So if our goal is to make x go to 0, okay, then these are multiplied to the errors. Okay, x minus x is the error, okay, the deviation from 0. So the larger these terms, you would expect that the control is going to act faster. Okay, it's going to be larger, and thus drive the system more quickly to 0 while attaining critical damping. Okay, so the control signals, right, will be that much larger. And you think, well, stronger controls, right? Makes the system go to 0 faster. Isn't that a good thing? Yes, it's a good thing. Okay. But if you make the gains too large, so several bad things can happen. Okay. One is that the motors, okay, they cannot produce infinite torques and infinite forces. They have limits. Okay. So the actuators might saturate. Okay, that's not a good thing. And if these are set too large, what can happen is that chattering can occur. Okay, so it's going, and then suddenly there's an error, small error. If these are large, it amplifies that small error by a large factor, so the control signal can chatter. Okay, it can go from one extreme to the other extreme. Okay, and that's kind of very wasteful, okay, energy-wise. And not only that, but it can also cause vibrations. Okay, so sometimes you may have seen, maybe in your experiments in mechatronics lab classes, right, you might have seen systems that vibrate a lot. Well, part of the reason for that vibration could be chattering in the control. Okay, the control is going from one extreme to the other very quickly. Okay. So there are practical limits to how large you can make kV and kp. Okay. All right. So we'll discuss that next time. I think this is a good place to stop now. So we'll stop here today.